Hello. Sorry, I didn't hear the response. The slide is visible, right?
Yes, sir. Yes.
Okay, fine. So we'll just continue from where we discussed yesterday. We are talking about the approach to similarity analysis. We have seen that the hypersonic equations envisage and sorry, envisage steady forms of the hypersonic equations can be written in terms of the small perturbations or small disturbances, that is in terms of the velocity disturbances caused in the various directions by the presence of a slender body because we are considering tau, that is the ratio of d to l, the transverse dimension divided by the streamwise dimension, to be a very small value, so that tau squared will be significantly less than 1 and it can be neglected. The way the equations are written are by using non-dimensionalization in such a way that it has terms of the order of magnitude 1 or order of magnitude tau squared. Once we come across equation for terms which are of the order of magnitude tau squared, since we limit our attention to slender bodies, we can neglect those terms because tau squared is going to be significantly less than 1. So by this practice, that is by non-dimensionalizing in such a way that they are the orders of magnitude will be either that of 1 or that of tau squared, and neglecting the terms which are of order of magnitude tau squared, we have a set of equations which are expressed in terms of x bar, y bar, z bar, u dash bar, etc., p bar, rho bar, etc., which are all non-dimensional forms. Okay, only the u and v terms we have used the perturbations. P and rho we have just retained as such by but with appropriate non-dimensionalization. So with that, we have a set of equations which are still nonlinear partial differential equations. So we are not attempting to solve them, but we are trying to study the behavior of them. And that's what takes us to what is called as similarity analysis. As I mentioned yesterday, similarity analysis in fundamental fluid mechanics, as well as in aerodynamics, and also in hypersonic aerodynamics, which we are talking about now. The similarity approach is common in its basic approach. That is, it considers flow situations which are similar in certain aspects, but have dissimilarities as well, but then strikes an equivalence between the two cases. I repeat, tries to strike an equivalence between two cases which are similar in certain aspects, but have certain dissimilarities. So by a proper restatement or reformulation of the governing equations, we try to uh, uh, strike an equivalence between non-dimensional parameters between two bodies which are similar in geometric shape, etc. So with this approach, now we have the set of equations. We have said we have discussed this approach also. Once we have the set of equations, the next step is to apply the boundary conditions accordingly. So let's have just look at the commonalities or the most important aspects of the equations that we have now. I'm just concluding or summarizing what we have discussed already. The application is only for steady inviscid flows because we have taken the forms, the equations in a way that is applicable to steady inviscid flows. We don't have transient term, we don't have the steady viscous forces either. So that's one restriction. Second is the application is only for hypersonic flows, because we have in many instances when we neglected the terms or considered them to be of the order of tau squared, etc., or of the order of which can be neglected, or of the order of unity, etc., we have restricted our attention to hypersonic flows where beta and theta are small, or in other words, theta is small and beta is of the same of similar magnitude as beta, and that we know why it comes to be so. But then we are restricting our attention to hypersonic flows where beta, the wave angle, is small, So and that concept is what we use in many terms like rho by rho infinity, p by p infinity, etc., where we took the limiting cases as m tends to infinity to non-dimensionalize the terms as well as uh, to do the order of magnitude analysis. So the whole analysis is based on m into m tends to infinity. So the way that we have written these equations is based on hypersonic hypersonic approximations. So study inviscid hypersonic flows. And the third condition is, as we have always said, we are looking at slender bodies. So slender bodies means tau squared is significantly less. That is, tau squared is much smaller than tau squared. Tau is smaller than 1. So needless to say, tau squared is going to be very less. So can be sort of negligible as compared to unity. So based on these three conditions, we have this set of equations which we have just seen yesterday. Now, coming to the boundary condition, how are we going to apply the boundary conditions? This velocity vector. Actually, on one side we have the body. So this we have discussed earlier also when we discussed about Mach number independence. U nx v ny w nz is equal to 0 because the flow is tangential at the body. It doesn't have a normal component. So the normal component in all the three directions can be equated to 0 because the flow is inviscid. So this condition applies for all inviscid flows. We are just adapting it here since we are continuing to consider inviscid flow. And we are now just rewriting that in terms of perturbed velocity components or in terms of velocity perturbations. So what we have written is u, nx, v, ny, etc. In the first box. The second one is just rewriting the same. Instead of u, I'm using v infinity plus u dash. U is the local velocity, and we know that the local velocity is nothing but v infinity plus the perturbation. So v infinity plus u dash. So that's a second step. Similarly, in the other two dimensions, since the initial velocity is 0, what we have is v dash and w dash respectively. So that's the two other components, v dash and w dash. So that's a perturbed form of, or rather perturbation form of boundary conditions as far as the velocity components are concerned. Now we consistently go for a non-dimensionalization approach because we are basing the analysis on a order of magnitude analysis. Order of magnitude analysis requires appropriate non-dimensionalization. So we are just rewriting the terms. Please take a look at the way that they are written. You can easily see that what I've written here as what is shown here in the box as 1 by tau squared plus u bar square u bar dash is equal to sorry, multiplied by v infinity tau squared into nx is nothing but this term u infinity plus u dash, because the new this one that we have used here u bar dash is based on the non-dimensionalization that we have discussed already. That is u that is equal to u sorry, u dash or u prime dash or u dash bar or whatever. U prime dash is equal to u dash divided by v infinity tau square. And just the same definition is being taken here to rewrite the equation using the non-dimensional form. So when you do that, it becomes the first term, for example, becomes 1 by tau squared minus u bar into v infinity tau squared multiplied by nx. So this is just one step incorporating the non-dimensionalized form of the perturbed velocities, non-dimensionalized form of the perturbed velocities. Similarly for v dash and w dash, they are the non to incorporate the non-dimensionalization. We have v prime dash, and to equate that to v dash, we have the multiplication by v infinity into tau, because that's a way that we have non-dimensionalized, or we have defined the parameter v bar dash. Similarly for w also. So with all these adaptation or non-dimensionalization, we can rewrite the energy. We can rewrite the boundary conditions for velocity as in the last box, as given in the last box. Yeah, nx bar plus v dash or ni ny plus w dash bar nz equal to 0. Ny and nz both are with bars because they are also non-dimensional. So the velocity vectors also that we are considering here are, say, like in the case of x, it is tau into nx, and in the other these ones they can be almost equal to the original values of y, because the perturbations in the directionality of them is small. So I mean the variation the in that is relatively small. So we have the boundary conditions now for the velocity components. We have the boundary conditions for the velocity components now, non-dimensionalized as well as written in the perturbation form, or rather we have put non-dimensionalized the perturbed velocity perturbation conditions appropriately, say consistently with the way that we have non-dimensionalized the equations also. So that's about velocity components, and obviously for other parameters like pressure and density, we are incorporating the hypersonic condition, that hypersonic plus similarity condition where beta tends to 0. That is, the angle of the wave angle is small, and theta is also small because of slenderness. So and because of hypersonic conditions, beta and theta approach very closely. So sine beta can be approximated to sine theta, and which can be approximated to theta, etc. So these are the usual hypersonic slender conditions that we have been always following, and incorporating those, the non-dimensionalized forms of pressure and density can be written as shown here. Please note that we are not including addition of physics here. We are just rewriting them using the relations that we have considered already. So for example, P2 by P infinity is the definition for P2 bar. Sorry, rho 2 by rho infinity, the density, non-dimensionalized density, is what we are calling as rho 2 bar. And we know that it takes a form gamma plus 1 into m infinity squared sine squared beta, etc. across the shock. And along with that, using the hypersonic simplification as well as the definition for sine beta, which we have used already, sine beta is equal to beta, and from the geometry we can incorporate tau into it. So dy bar by dx bar at the surface. So with that, we can rewrite rho, or rather the non-dimensionalized form of rho bar or rho 2 bar, as gamma plus 1 by gamma minus 1 into etc. etc. Please note that dy bar by dx bar in this comes from the consideration of the velocity, or more precisely, consideration of the geometry, or more precisely by connecting the geometry to the wave angle beta in terms of the sine of it, sine beta. So by the same approach, we can write rho 2 bar, P2 bar, both of them in terms of the modified parameters, the non-dimensional parameters, and similarly the velocity perturbations after the shock. So what we discussed in the previous slide was, this slide was the surface conditions for velocity. What we are discussing here are on the other side, that is on the shock side. So the shock side, we have looked at the pressure, density, and also the u2 dash and v2 dash, and non-dimensional forms of it, u2 prime dash and v2 prime dash, which all can be written, or which are can be written in the way it is shown here by using the relations that are shown on top. Now, if you look at these, keep in mind we are now looking at the boundary conditions on the other side, that is on the shock side, and you can see that in all of them, the way Mach number appears is as a product of Mach number and tau, or wherever you see Mach number in these, we have along with that tau also. Say for example, in rho 2 prime, you have in the denominator m infinity square tau square. Similarly, in the case of rho 2 P2 bar also, U2 bar also, U2 prime, this one also, that is the perturbation of velocity as well as perturbation of the y velocity V2 prime also. In all these, we see that the Mach number shows up as m infinity square tau square, m infinity square tau square, all these. Okay, so we don't see Mach number independently in these in the boundary conditions here, and of course in here we don't have Mach number at all. We have all in terms of velocity components, and yeah, we have equations we have seen already. So because of this product m infinity into tau is referred to as a hypersonic similarity parameter. Why do we call it as a similarity parameter? We'll be able to appreciate that further as we go forward. But it's a similarity parameter because if we are able to maintain m infinity into tau, because the Mach number, free stream Mach number comes to the boundary conditions only as m infinity into tau. So if we are maintaining that product as the same, then we can have, for two different conditions, we can have similar solutions. For two different conditions, we can have similar solution. And that's why we call it as m infinity into tau as a hypersonic similarity parameter. That is, to put it in another, this one, even if Mach number is different and tau is different for two different cases. Let's assume that we are studying two bodies, geometrically similar bodies. In one, Mach number is m1 and tau is tau1. In the other, Mach number is m2 and tau is tau2. But as long as the product is the same, that is, as long as m1 into tau is equal to tau1 is equal to m2 into tau2, we can get the non-dimensional solutions equally in both cases. That's why it is called as hypersonic similar. That's why it is called a similarity parameter. In fact, if you recall, this is the reason why in fluid mechanics we call, or we can call, Reynolds number as a similarity parameter in say in several applications. It's all because of this. That is, it's a if you maintain that parameter the same, even if the individual components vary, you will get the same value for measurement for the non-dimensional measurements, non-dimensionally defined variables. Okay, so m infinity into tau is the hypersonic similarity parameter. We'll look at it more detail. Now, as I said, we are not solving the equation. We cannot solve them. We cannot solve them analytically. We can look at the nature of the solution. We can probably guess what is going to be the behavior of the solutions. We cannot solve them analytically because they are still strongly coupled nonlinear partial differential equations. No closed form solution available. But then we can see what if we were to solve them, what could be the type of solutions that we get. I scribbled them here on the in these three relations. For example, if you were to solve these equations, again, if you were to solve these equations, what are the equations? They are equations for rho, u prime dash, v prime dash, etc. And p bar. Sorry, rho bar, p bar, and the three velocity components. I repeat, they are equations for rho bar, p bar, and the three perturbed velocity components in their non-dimensional form. So if I were to solve them, then I can get the answers in terms of functions for what I would get are the solutions for p bar, rho bar, and the velocity components. I would just written u bar here. Similarly for w and v. So I can get non-dimensional velocity, non-dimensional pressure p bar, non-dimensional density rho bar, and the non-dimensional velocity component u bar, the perturbed one. And then all of them will be a function of x bar, y bar, gamma, m infinity tau. Why are we saying so? Because all the equations have x bar, y bar, and gamma, and in all of them we see m infinity into tau. That is the product. The boundary conditions are in terms of m infinity and tau. So the result, if you were to actually solve them, the functional results will be into each of them will be a different function for. It's not that they are all the same functions. P bar will be a function, rho bar will be a different function. Obviously, U will be a different function also. So, but they will all have the variables, the independent variables x bar, y bar, gamma, m infinity, and flow. So, this will be the type of solutions that we get, which in turn means that, before I go to this huge text here, I guess we can readily reach the conclusion here. If I have the same value, if I have two different conditions, and if I were to look at the same location of x bar, which is defined by x bar and y bar, and if I have gamma being the same for them, for the two cases, then if m infinity into tau is this, what I had mentioned earlier, if m infinity into tau is the same for the two cases, then p bar is going to be the same. I will repeat this. I request you to just stare at this equation and see whether what I say is making sense to you. If not, I can try to explain it further. Well, we just focus on P bar, the non-dimensionalized pressure. Forget about the definition of it. We have looked at the definition several times, P by gamma infinity squared, etc. But for now, just take it as the non-dimensional static pressure in the flow field. The non-dimensional static pressure in the flow field. What we see here is that we can express it as a function of the non-dimensionalized value for x, y, and the gamma, and the product of m infinity and tau. Now, so if I have this solution for two different conditions, what I'm saying is that case 1, case 2, assuming that we have two different geometrically similar conditions, then what this statement says is that in two bodies, so I suppose that I have one body like this, and if I define a point on it, a point P, which I can mark by their corresponding coordinates x and y. For now, just consider a two-dimensional body. I can mark the point as x and y. And I have a similar body, similar, geometrically similar, but maybe with a different thickness, etc. In that also, I'm looking at another point, Q. And let's assume that they happen to have the same values for non-dimensional parameters of x and y. I repeat that non-dimensional values for x and y. So it's not that they are having the same values for x and y. That is the points P and Q. I'm saying that they have same values for non-dimensionalized values of x and y. That is x bar and y bar. If so, assuming that we are having the same working fluid, say like air, where gamma is the same, then we can say that as long as this product is the same for density, similarly for the velocity field also. So all pressure distribution, the non-dimensional pressure distribution, non-dimensional velocity distribution, non-dimensional density distribution, they are all going to be the same as long as m infinity into tau is same for the two cases. And this is the statement of hypersonic similarity. That is, I just complete the. We are considering similar bodies. That is, they are the shape is similar, and maybe in one dimension there is a change. So, for example, I have just shown these two kind of that greenish arrow kind of bodies, arrow-shaped bodies, in which you can readily notice that the thickness is different, but the shape is the same, and the length in the x direction they have the same same comparable length. These kind of bodies are referred to as affinely related bodies in similarity analysis. We probably would have come across that term already. Affinely related. Affinely related means the geometry is similar, but maybe in one dimension there is a change in the scale. That is, the shape is similar, but in one dimension there is a change in dimension. That change in one direction there is a change in dimension or scale. So that is what by an affinely related set of bodies. Okay. So what we are saying is that I am just now going to read from the text there. Okay. Solutions for two different flows over two different bodies with similar geometry but different scale in one dimension, which is what we call as affinely related bodies. The solutions will lead to the same values of non-dimensional perturbed components. The solutions will provide the same values for perturbed velocity components v dash and u dash, whatever v prime dash and u prime dash, provided that they are having the same value of m infinity into tau. M infinity into tau, which is the similarity parameter we usually indicated by k. Okay, so the box that on the top is like, if you are looking at two hypersonic bodies with similar shapes, but maybe a difference in the transverse direction, then the velocity field around them in terms of the non-dimensional parameter v bar and u bar can be the same, will lead to the same values of the non-dimensional velocity field. Keep in mind, I'm not saying that the velocity will be the same. I'm not saying that u velocity will be same. I'm not saying v velocity will be same. I'm saying that the non-dimensionalized form, that is the u bar by v infinity, v infinity, etc., will be the same. So the non-dimensional velocity field will be same if both are exposed to flow conditions where m infinity into tau is the same. Why do we say m infinity into tau is the same? Tau is different for the two bodies, right? D by L, because of the difference in the transverse dimension. D by L is different for the two bodies. So you may have tau 1 and tau 2 for two bodies, but and they are exposed to different Mach numbers. But as long as m infinity 1 into tau 1 is equal to m infinity 2 into tau 2, then the velocity field around them will be similar or will be equal. That's what is meant by the statement of hypersonic, or that is the statement of hypersonic similarity, and it can be applied to many bodies of interest in hypersonic air breathing propulsion. As we have discussed already, they tend to be slender bodies from based on the know-how that we have in the global body of literature. In hypersonic propulsion, the bodies need to be slender. So when in such applications, the pressure distribution or the flow distribution can be solved approximately under envisaged transient conditions by using the the similarity approach. So that's what we make use of in doing some initial estimates of what is going to be the relative comparison of flow field between two different designs. So that's basically the applicability of this concept. Before I pause for your, so far, if there is any question, I'm not sure how much I've made these things clear, but I'm optimistic that if you go through the slides once again, that any questions, by the way? If not, I'll just complete this part and then we can pause again. As much as I can, actually. Yeah. Now, just an addition to this, so far we have been always considering bodies without angle of attack, but it has been shown that now I'm leaving all that mathematics here, all that analysis here, but the studies, actually there are papers, actually, some of them I have seen also, fairly old papers, but in that they have also shown that even for angles of attack, for small values of angles of attack, the similarity holds good in the modified fashion as it is shown here, in terms of when the Mach number, when the angle of attack is expressed in terms of alpha by tau, the similarity still holds good, which means that m infinity into tau, n infinity into tau, and alpha by tau are similarity parameters when alpha is not equal to 0. I repeat that for non-zero angle of attack, as long as the angle of attack is small, the two similarity parameters will be m infinity into tau and alpha by tau, which means that if you have, again, so you have affinely related bodies exposed to different flow conditions, but if they have m infinity into tau and alpha by tau be the same for the two, then they will have same pressure distribution, density distribution, non-dimensionalized pressure distribution, density distribution, velocity distribution, etc. So since pressure P bar can be related to Cp very easily, you can just go through this one. It's just algebra that is relating P bar to Cp. This means that we can have Cp value related, that is coefficient of pressure can be equated in terms of P by whatever we have been always calling as P bar, and this has been proven using say like numerical methods, where they've seen that if you do an analysis for two different bodies, you do a modeling for two different bodies which are affinely related, that is they have similar shape but they have a difference in the transverse direction. If you do that and if you expose them to two different Mach numbers, say one is m infinity equals 3 and the other is m infinity equals 6. So this 3 actually is questionable because it's not in the hypersonic range or this one, but for very slender angles it can just move to lower, it can apply to lower hypersonic values also, I'm sorry, lower values of Mach number also. So that's only justification for m infinity being 3 here. But then more importantly, m infinity into tau being the same for both cases. Okay, so they have chosen it in such a way that k, the m infinity into tau, is equal in both cases. So when you do the analysis, you see that for two bodies, the non-dimensionalized parameter Cp, actually it's the way it is plotted is by multiplying by k, etc. Anyway, it's all non-dimensional. So what matters there is Cp. So the non-dimensionalized value of Cp for the two cases, say the circle one is this circle one, that is the Mach 3 one, is this one, and the square one, the Mach 6 one, that is for the other body. They fall on the same line, which means that the non-dimensionalized pressure distribution is practically the same, which sort of validates what we are talking about in terms of the similarity argument. And this also is from a paper. This paper also it's an ancient one. I have this one of it, but then that is the finding of them, or how that is how they are corroborating the arguments of hypersonic flow similarity to more detailed exact calculations. And there are some experimental data also which corroborates. I'm not going to the description of this, but just remember that, or just keep in mind that these are experiments done for two different conical shapes, and the data is plotted under I don't remember the Mach number in this, some hypersonic values. They've written here actually 4.46, etc. Slightly in that range. So in that also they have seen that, so if you see each of these curves, it's actually pressure measurements done by having static pressure probes placed around the body at different locations. But for each curve, you can see that the points with trying to relate it, the flagged ones and the unflagged ones, they are the two different cones and the location, the data for the for cone 1 and cone 2. They for each of these you can see that flagged and unflagged, flagged and unflagged. Okay. They all fall, the flagged and unflagged for each case, that is for each angle, they fall on the same curve. This is a kind of validation for this whole argument of hypersonic similarity. So within the limitations of this theory and the applicability of it, it's fairly useful in correlating to what can be actually expected in basic design shape. So that's where the applicability of this concept is. I'll definitely stop here now. If you have any questions, please. In fact, the importance of such arguments, hypersonic similarity, and also to some extent Mach number independence, etc., the importance of them, practical importance of them, were more in a few decades back when experiments were even more difficult than they are today, and also numerical methods were not so developed. Even now, experiments continue to be very difficult in hypersonic flow, but then we have the help of CFD, which is advanced in terms of its capability, physics, as well as the runtime, etc. So right now we have a helping hand from CFD. Yeah, but when it was not there, or it was not so developed, this the theoretical models were more useful in practical analysis. But now, even though we have we have the help of CFD, the applicability or the importance or the significance of this similarity analysis, Mach number independence, etc., continue to be there, because these are, even for numerical modeling, to get initial estimates of what the expected patterns and to provide more insight to the variations that one would expect. These analyses are important, and that's the reason why even now you can see the applications of these in several papers that are being published in hypersonic flow research. I stop here. Any question? No, okay. So as I mentioned, if once you go through the presentations independently, if you have anything to be discussed further, we can take them up later. So for now, we'll stop it here, and see you in the next class. Thank you and bye.
Thank you.